start. Cool. All right. So today we are very happy to have Xuereb from Atom Institute from TU Van to talk about knowledge in thermodynamics. And now is your time.
Thanks for coming.
Just mention that we are recording.
Oh, yeah. And also, by the way, today we will record the seminar talk.
Okay.
Yes.
Thanks for coming and thanks everyone, for the invitation. Bristol is a very cool place for on thermo, somehow also a bit historic from Bridge onwards, and like all these people like Ralph and my supervisor Marcus was also over here for his first postdoc and so on. So a lot of kind of ideas in quantum thermo where it's or the second age of quantum thermo, if you like, we can talk about the history after. We're born here, and it's also, I don't know, a very pretty city, very cozy. So I'm very happy to have this challenge groups in by the BQIT. So today I will talk to you about this arXiv posting we had recently. So this is the number. With the title, what resources do agents need to acquire knowledge? And this word knowledge is a bit ominous, no? Like it can mean many things. So we should maybe start by discussing what it would even mean to talk about knowledge of a quantum system. So if we imagine that we had some, I don't know, gas of quantum particles, like very many of them or whatever, and that this was our quantum system of choice, that, maybe if you did some like tomographic process and you obtain the density matrix representation of the state of the system, that you have knowledge of it, right? But this is a classical representation of a quantum state, okay? So we did a bunch of classical operations. Maybe we had some very nice POBM, we did many rounds, we got the density matrix, but in some sense, it is just a matrix you can write down on a piece of paper. If there was, let's say, some kind of a quantum agent that wanted to do actions on the state of the system, this tomography doesn't really help them. Similarly, we're doing quantum thermo, so maybe we want to assume that this is in some thermal state. So maybe rho s, we know a priori is going to be in some state like this. So what if instead you did metrology? And with like the promise of the Hamiltonian, you can also determine like classically a representation of this state. I think this also does not help such a demon, such an agent that wants to act on the system. And this is a bit our like starting point for this kind of type of interrogation. So what we will need is a third system or a third object, right? The system, the agent, a memory. So some quantum memory where, again, you have a quantum system, but this time the agent has some, crazy great degree of control over the system. And what I would like to convince you of, and actually the fourth thing as well, a probe, what I would like to convince you of in this talk is that the knowledge an agent has of a state of a quantum system, I think could be well represented by the agent's ability to sort of unitarily recreate the state of the system in some memory they have access. And also with access to some probe quantum system. Okay, so how do these things play together? And why is this reasonable? I also want to mention this kind of I don't know how many of you know the last Blackboard of Richard Feynman, but there was this quote, which of course had nothing to do with this, but it said, what I cannot create, I do not understand. And in some sense, so this approach kind of agrees with this, no? That if the agent wants to know the state of the system, having knowledge of the state of the system should be the ability to recreate that state. Maybe also classically, if you say know a document, if you have a file on your computer, you should be able to copy it, right? But here is the sort of quantum crux, right? Like we cannot copy things. There is the no cloning theorem, and somehow this whole thing is a dance around the no cloning theorem and these types of things. So let's see how we will get into that. So yeah, yes.
To be clear, you would be happy if I just teleported the state into the memory,
I would be.
and you say that would be knowledge.
Yes, but not just teleport. Sorry, right. So yes, there's a bunch of caveats here. We don't want to perturb the state of the system, maybe, right? So we want to be able to copy and not just teleport. And maybe one good thing to mention here is that the probe, how it is limited and its ability to kind of copy this information, has in some sense, this problem has already been studied a bit. Because in the case of thermal states, you just have classical information in one basis, right? You have the set of populations, you want to move these populations to somewhere else. And in this paper by Jelena Guryanova, who, I mean, also did her PhD here, they study how, in some sense, that problem, like measuring a quantum system and redundantly putting that classical information into a probe system, is limited by temperature. So that would be this one. And whilst, so like kind of temperature limited probes. And whilst that's cool, what I would like to tell you about is how I think that the dimension of the probe is a much more important quantity than the temperature, because it directly corresponds to how coarse-grained a POVM is. So indeed, let's start with an example to see this. So let's imagine that there is some putrid system with some populations P0, P1, P2, and I will, like, if there is a diagonal density matrix, I will write it down as a vector a lot of the times. And so we can imagine like that there is some agent one who has access to, and yeah, let's say that this has some, like, some Hamiltonian over the basis like 0, 0, some eigenvalue, 1, 1, and 2, 2. So if there is like agent 1 who has access to POVM elements, which are the projectors onto the energy eigen states, then of course agent 1 correctly estimates the state. So agent 1 obtains P0, P1, and P2 as an estimate. But now imagine there is some second agent, and they have access to this POVM instead. And the same thing again. So this is an agent who, in some sense, is confusing the first and second energy levels, and they will obtain P0, P1 plus P2 on 2, and P1 plus P2 on 2. Okay, so these are nice POVMs, but how can we understand these things physically? So, and what do I mean by physically? I just mean I would like a unitary model. So for agent one, this is pretty easy because as we were kind of discussing, agent one like is fully able to clone and copy. And why? Because a thermal state is just a classical distribution on one basis. So if I give agent one a 3-level pure state, and the agent does some unitary on the system and the probe, which will be something like this. So if I'm in the energy level I in the Qtrit, I will rotate the 0 state into I. Yeah. Identity on the red. And in doing so, we take this kind of tensor product of P0, P1, P2, which is the system, and some 1, 0, 0, which is the probe. And then when I'm in here, I rotate this guy. Well, I actually leave it there, but if I'm in here, I rotate like P1 of the population down into there, and P2 of the population down to there, all good. And again, why can you do this? Well, this is mega pure, so I don't have enough entropy, I don't have enough entropy stopping me from like moving this population, this distribution of populations around in the way I would like, right? And I can turn this distribution into anyone that's of lower entropy. And there exists a unitary that does this. And again, no cloning doesn't impede us here because we're doing it in a single basis. More generally, state estimation and cloning are a related thing. Like the best POVM for state estimation turns out to have the same form as the universal cloner, and asymptotically they are equivalent tasks. And this is sort of a result of Tony Asin and John Mubai from 2005, and it was a peer. But I mean, the relationship was pointed out earlier in the 90s as well. So what about agent 2, right? Like physically, what's going on with agent 2? So one way we can think of what is happening to agent 2 is we also give agent 2 a pure state, but this time, let's say it's a qubit. And we will do a unitary, which if I am in the 0 state in the system, so in this Qtrit system I'm trying to estimate, I will do nothing, so I don't move the population. But if I'm in, if I'm in the first excited state or the second one, I will do a sigma x. And those of you that know what a von Neumann measurement is, this is exactly that. It's nothing super new. But what happens here? So we go from this state 1, 0 in the qubit to this state P0, P1 plus P2 in this probe state. And so we've mixed up the populations of 1, 1, 2, 2 here. We don't know where, like we know that their sum is P1 plus P2, but we don't know how they're distributed, right? And so agent 2 kind of runs into this problem. And now agent 2 wants to propagate this information into a Qtrit memory, right? Because they want a fair comparison between a Qtrit and the Qtrit. And what this agent does is that they will take their probe and let's give them access to this Qtrit memory also in an all 0 state, so it's empty. And now we want to end up with a memory state which takes this form, which is the same thing which we got out of the coarse-grained POVM over there. And so what you will notice here is sort of that the agent learned this sum, P1 plus P2, but we want to distribute the information with least assumptions. kind of a bit like James' principle, right? Like we don't want to say that, I don't know, P1 plus P2, maybe we put 2/3 of it in the first population and 1/3 in the bottom. We want to really assume we knew nothing and we distribute it equally. And this is possible, but I'm not gonna run you through how the joint unitary on here and here works. What I will tell you is that all it involves is basically a global operation on P and N, which first involves kind of like permuting these populations on the diagonal. Tony?
You think there was a problem that, you know, you interested in the eigenvalues, so you using to change eigenvalues.
No, yes, yes. Okay. Look, I'll try to do this as quickly as possible without getting stuck, because I know myself and I will want to get stuck here. Okay, so okay, so we have the P0 is going to appear here, and we have P1 plus P2 is here. Okay, happy with this? So now, and this is the joint state of probe and memory. Okay, so now what do? We put this guy up here first. It's a two-level swap, all good. So I'm gonna rub this off. And now we're gonna do a Hadamard operation, but we're gonna do the Hadamard across this and this guy. So it's a non-local operation. And now we end up with, is that true? No, let me check.
I mean, you're saying that this, okay, this reduced the of that.
Yeah, that's the reduced state of the memory.
Effectively.
Okay, but like, let me quickly, yeah, so actually I do it with 1, 2. And I don't know, this line should have been here. Anyway, you get P1 plus P2, 1, 2 here, 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 and here. And so the marginal on the memory is, this is the first contribution, the sum of these two. This and this is the second contribution, so the second population, and then the sum of this and this is the third population. That's how you get that. And the important thing, which also appears in the general case, is that this Hadamard, we had to do it in this 0, 1, 1, 2 subspace, where notice that the indices never repeat. They're always +1 away from each other. And that's how we ensure that in the memory, we get an estimate, which is diagonal. Okay, we need the coherences that we're going to use to kind of distribute this information to go away after we trace out. And this is kind of the thing that makes this procedure challenging. But cool, okay. So we have found a unitary way to represent this coarse-grained state estimation. So a coarse-grained state estimation, we can always relate to a unitary procedure in 2 steps, okay? And what are these 2 steps? So step 1 is information extraction. So like imagine that there is some D-level system, it's in a thermal state. And now we do this UIE, which is information extraction, where UIE is nothing more than a set of conditional rotations. Okay, so or yeah, conditional permutations of the basis kits. But it's conditional on the system, so we don't perturb the system. So we're allowed to do this many times if we want to, because we're leaving the system in the same state. Okay, and from here, what do we get? We sort of act on the system and the probe, and then the probe will be in some state which is like sums of these populations. So I have these P bar guys, and I'm going to explain what they are. So here, imagine that the system is d-dimensional, and here I have the probe, which is k-dimensional, such that you know, K is less than D. And then I run into a bit of like a combinatorial game, because basically I have D objects in there. And I have to group these into K objects. So maybe I can use these symbols. But of course, there's going to be very many choices for how to make these groupings. And this is going to be a part of the game. So to keep track of that, we will use something called like a T vector, which is nothing more than a K tuple, where I have these numbers T0, T1, blah, 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 up to Tk minus 1, which indicate which coupling I've chosen between the system and the memory, okay? And so this is, yeah, it's a K tuple, which sums to D. Let me make that a bit more explicit by returning to the example of the qubit and the qubit. So imagine, or not imagine, right? What do we have? We have 3 energy levels of the system, 2 energy levels of the probe. And there are 3 options of how to couple these guys, right? So first, we can couple the first level to the first level and the other two to that level, or we can couple the second one to the top one, and we put these ones here, or we can couple the bottom one to there and obtain 2 here. Okay, so in doing this procedure of trying to learn the state of the system through correlations, there's going to be 3 different outcomes we can get, right? So 3 different so-called estimate states, okay, which would look like this. So in the first one, the one that we just saw, the agent correctly learns the first population, but mixes up the other 2. In the next one, they learn the second population, but mix up the other 2. And in the third one, they learn 2, and you kind of get the pattern. Okay? So what this T vector is doing is counting how many such possibilities I have in general. Why do I want to do this? Because so we've seen that the first step is a conditional unitary on the system that doesn't perturb the system. So I want to ask now, how many probes do I need? How many couplings do I need to get how many estimates, to maybe manipulate the estimates and get as good of an estimate as I can of the state of the system? This is kind of the game we want to play here. So yeah, for the interested nerdy people, K tuples that sum to a given number. This is like a well-studied combinatorial thing you might have done in your undergrad. And in particular here, we will have m such estimates. If there is repetition, we need to add some r, which makes the overcounting go away. And we will have d multi-choose the T vector, which is nothing more than kind of this quantity, one up to T K minus 1. And yeah, I mean, this is just, I mean, d factorial over the product of all these factorials. I mean, it doesn't matter massively. But there is going to be m estimates in a general scenario. Okay, so that's the first part, this information extraction. It's a conditional unitary which doesn't perturb this guy and creates these kind of averages or sums of the populations from here, right? Paul.
So this doesn't look like the most general thing you could do, even with Richard's dimension.
Okay.
On purpose.
Do you want to do coherent things?
No, but even like different mixings, right? Like you're preserving one and then you're completely randomizing the rest. Like
Yeah.
potentially like do arbitrary mixtures and keep some amount of something and then
I mean, let me think of an example. Yeah, if we have like a 4-level system, okay, and a qubit, then T vectors we can have 1 and 3, or we can have 2 and 2, for example. Do these two situations capture the two possibilities you have in mind here?
I don't think so. So in your example, you've got P
Yes.
naught, and then you've got P1 plus P2, and
Yes.
P1 plus P2.
Yes.
But could you imagine a situation where you saw something like P1 plus P0 plus P1, P1 plus P2, and like you've got something a bit more like a different type of information about the state. So I think you're preserving one and you're completely mixing the other two.
Yes. I think in the Qtrit, I think in the Qtrit, that's the type of, say, confusion I was envisaging, but it's because of this grouping game, right? Like if you have 3 things here and 2 things here, in how many ways can you make 3 things talk to 2 things?
I guess I'm wondering a different type of interaction.
Okay.
So imagine the final vector is P0 plus P1 over 2, P1 plus P2 over 2, and then P2 plus P0 over 2.
Yes.
That's like this all 3 levels are somehow mixed.
Yes.
I've got partial knowledge about all the
Yes.
partial stuff.
So I think you are correct in that the agent is not so bad at this game. We are like, there is some strategy that the agent kind of knows the grouping that they are doing, right? Like the agent knows that they have a k-dimensional thing and that the system is a p-dimensional thing. And then they say, well, okay, I can't do anything special, but I can fix a coupling, like I can fix, that I send 1 energy level to 1 energy level and 3 to the other one in a qubit, or 2 to 1 level and 2 to 1 level, and I'll just fix a coupling and do all of them, and then see how well I do. That's kind of the one we take. But I guess what you are pointing out is that already this is.
I'm just wondering if it's obviously these are the smartest things you can do given the restriction on the dimension, or if the thing I'm suggesting, like, could you show that what I'm suggesting is just somehow uniformly worse?
I'm uncertain, but happy to look into it. It's not something I thought of, right? So yeah, maybe I can understand it a bit better. But yeah, I don't know. For me, this T vector thing was.
I agree. Wondering.
Yes. Yeah. Then for now, I do not know. But I would say maybe that's also a bit of a general remark. Like in my group, no one really is doing this type of, playing with POVMs, state estimation type of thing. So like no one really wanted to push up against this stuff. But I would be very keen on what you guys have to say about that point.
Also, can I check? So is that kind of an assumption that you're only going to do the POVM once?
Yeah, and then move on to the next. Like so, here you can imagine that in the next case, corresponding to this one, you have 0, 0 plus 2, 2 on 2, and then the 1, 1 is there, and then do each once. So it's like the agent, in some sense, I don't know, in a given round, he doesn't know what he's going to get, but he knows he has 3 and 2, and like if he does them 3 times, he will get each thing in each possible coupling. Okay, I don't know if I'm being clear or confusing, but let's see. Right, so we had the information extraction step. And next is the estimate generation step, where we take the information we learned and we spread it out in this memory with least assumptions. So basically, this P bar over 0, there's T0 terms in that sum. So then I take P bar over 0, I divide it by T0, I make sure there's T0 of those, and I move on to the next grouping and so on. So this level of detail is maybe not so important for the people that are not interested, but I will give it anyway. and so on. So you would get every grouping here in the memory. And that would be one estimate. And you can repeat this n times, where n comes from here. Okay, one thing to note is that the interaction you do between the probe and the memory is going to be highly coherent. So you're doing basically, here we had this Hadamard thing over 0, 1, and 2, 1, or whatever it was. And we needed that these basis kits that generate the subspace are kind of far away from each other in indices, so the correlations don't build on the memory. And what you end up with is basically the same thing, but with quantum Fourier transforms, and you need to kind of, again, keep track of these indices. So that's how that game becomes difficult. Okay, but now let's say we obtain some estimates, and now we want to see how well we can recover the state of the system with access to some estimates. So we can call this kind of part estimate manipulation. And you can see that there's two ways to do this. So if I have like omega bar, which is the product of all of the estimates that I was able to generate. So in the last example, we had 3. And I want to do some global unitary V on this product of these guys. And I can do 2 types of things, right? I can basically either spread the information across all of them equally, so kind of like a symmetric approach, where each estimate improves or stays the same in terms of how well it represents the state. And I get m of them, m good estimates, or an asymmetric approach, where I try to put all kind of the good information in one marginal, one estimate, and I don't care what happens to the rest. And in the second situation, you will see that sometimes when a condition is fulfilled, you can exactly recover the state of the system, if you act asymmetrically. In the symmetric case, of course, you cannot. So let us see what the symmetric case is like. Good. So maybe let me give an example with the Qtrit thing again. So I'm interested in doing the following thing, right? So I want to trace over any two guys in here, because I'm considering products like omega 0, omega 1, omega 2. But I symmetrize, okay? So I do a thing like this. And this is like the projector onto the symmetric subspace. What does that mean? That means that I basically run through every possible permutation. Sorry, I want to trace out over 2 of them to get one of them, because I want to look at how good one is. But I will get anyway. So how do these projectors work, right? If I have 3 possible estimates, in this they will run from 0 to 2. And I want to get every possible one of them. So I set this condition such that each one is unique, and there are omega I, omega j, and omega k, and I have to normalize this. So you will get a 3 factorial. In general, the projector onto the symmetric subspace like takes every possible permutation. It does every permutation of these guys, and then divides by, if there's n of them, n factorial, right? That's the number of permutations. And now we want to trace out over j and k. So one trick we can do is basically we can fix one of them, okay? So in this case, I can fix I, the first one. So instead of, 3 factorial is 6. So I can take kind of, maybe I should keep this inside the bracket. I can take the I fix it, but if I fix I still have I have 3 possible options. Okay, so I will still have to sum over I, but I can sort of take it outside from the rest. And then in here, I'm going to have the J and the K. And they have two options because I'm just permuting two objects. Right? And I still have this condition. Okay, but since I'm tracing out over J and K, and I have a trace over a tensor product, I can split this, and it's a partial trace. And so I trace over this, which is a valid state. So this goes to 1, like trace of a state is 1, and I'm stuck with this thing outside of the partial trace. So in general, when I symmetrize over omega, where I have m estimates, and I'm doing some like I am omega bar, which is the product of all of these guys, and I trace over m minus 1 of them, any m minus 1 of them. In general, I will get like 1 over m sum over omega I with omega I in O. So it's easy to find out what the state of the symmetrized margin is going to be. So there's going to be m of these guys. Nice, we have a nice prescriptive way of finding this out. Is it useful for anything? Maybe before I tell you if it's useful for anything, I can tell you what two guys of this type look like. So imagine I had a D-level system and I had a qubit probe. Then the T vectors I have at my disposal are 1 and D minus 1. So one where I put one energy level with one energy level of the qubit, and then D minus 1 with the others. And then I can also have D over 2 and D over 2 as like the extremal examples. Of course, there's like any other option in between these two guys. And what do the states that correspond to these look like? The symmetrized states. I will have the following. The one on and in the other case, it's kind of combinatorially interesting. Anyway, maybe it doesn't matter so much what it is. These are multi-choose things. So the point is, you will get the state plus something and the identity, like a mixture. This, by the way, is what people get out of universal cloning as well. So like if you put a pure state in a universal cloner and you try to get an approximation out of it, you will get a state which looks like, psi psi and like a 1 minus eta plus eta, the identity. And of course, here we're working with mixed states, so it's different. And by the way, this eta, they call it the black cow factor, which I think is very cool. So you can find this term in these papers by like Werner and Chiara Machiavello and other people. And it's called that way because they wrote these papers in this Black Cow Cafe in New York, which I think is funny. And you see here that it looks like a bit the same. It's less even. And why? It's kind of because we're giving the system, m copies of the estimates, but each estimate is like a copy that has been perturbed by the same amount in a different place. And that's kind of why you get these things out. Is this useful for anything? Well, to begin with, the fidelities you get out are not so bad. So let's take the fidelity with like a 6-level thermal state with an equidistant spectrum. If so, in this scenario, let's say we have T equals 1, 2, 3. So we have a Q-trid probe, and let's compare that with a qubit probe, where we have 1, 5. Okay, so what you will find is that the fidelity, and here I'm varying temperature on the x-axis. So I have a 6-level thermal state with an equidistant spectrum. I'm going to vary the temperature, and I want to see how good the symmetrized estimate is at reproducing this thing, right? Behaving like this thing. And basically, you get some like threshold behavior. So like here, there's this 0.3, and like, of course, when beta is 0, so it's the maximum mixed state, it's all good, right? Like fidelity 1. But this guy, as we get more and more pure, will go. So I don't know if this is 5 or whatever. Sort of has a threshold at 0.3. The Q-trid guy, I maybe should have drawn this a bit better. So the slope of this one is worse. The Q-trid guy does better for longer, and also the threshold is 0.5. I apologize for my, yeah. Okay, so if you have a probe of more dimension, you will do better for more states, and you also do better at first. So more dimension, better. We expected this because it corresponds to a better POVM, right? And
What's happening here? And then you take it down very large, the number of estimates.
So good question. So the system has D equals 6, K, the dimension of the probe, in the first case is 3, and the dimension of the other one is 2. We have T here, which is 1, 2, 3. And here we have T 1 and 5. So in general, in this case, you have M equals 6 multi-choose 1, 2, 3. And here you have 6, 6 choose 5, basically. I think this number is bigger, but off the top of my head, I can't tell you the number right now. Do you have a question?
And how have you compared what would be the difference between a 4-level system and 2 2-level systems?
You mean if I use 2 probes?
Yeah, like two probes.
I have not used 2 probes.
You've not considered multiple probes yet.
But very good point. No. Okay, I know Paul has to leave really soon, so I wanna.
Yeah.
So
Sorry.
wait,
No,
no, it's my fault. I spent too long talking about things that aren't important. Okay. Of course, as you scale the system, it gets worse, to be expected. Interestingly, if you use the symmetrized estimate state to try to extract the most amount of work from the system, you behave almost optimally. So it is as if you knew the state of the system, even with a qubit probe, okay? I can explain this later, but yeah. So symmetrized estimate gives you enough knowledge to extract work optimally. One estimate, you do extremely poorly. Now, the one last thing I want to try to get to is the asymmetric case. Yes.
On the top there, when you've got the estimate, and you've got this omega bar is the omega naught, it's omega 1, it's the omega.
Yeah.
So in the qubit probe, are you also just giving you like a smaller state? Is that what you're saying? You're giving me fewer copies because there are fewer different variations, or like like the qubit versus Q-trid?
Yeah, I think it has less. You couple less times because there are less options. Like we do all the couplings, but we do them once.
Every coupling, so therefore, in some way, you're giving yourself extra resource, right? So we're probing more tightly. In the case of the Q-trid probe,
yes,
because of the combinatorial factor,
yes,
it's actually just giving you more.
Yes, this is true, but I think we take the probe to kind of be a way to express how well the agent can interact with the system. And I think that's why I just let it do it once. But I think you're right that there could be smarter things the agent could do.
Because it feels, I mean, we were at different one with this. Noah and I had this paper recently about showing that even the measurement you consider here, the one with two outcomes, this can, in a certain sense, simulate a perfect measurement.
Okay.
If you allow to perform this measurement.
But with like classical post-processing or
well, so the idea is you bring in ancillars and entangle and then measure all the copies.
Okay.
So you give me one copy of the system, but you do that, you perform that measurement, say n times in parallel, and that is, we showed that it, it can reproduce at one moment. And so it feels related, but
I mean, so in the asymmetric case, maybe that's what we're going to do, right? Like we're going to do some global unitary on this product of these guys. And because this is like symmetrizing is a very local operation, it's just you just permute. And so, but if now, and then we're going to trace out this time, not over any m-1, but from like 1 to m-1. Okay, and we just ask, does there exist a V such that I can get rho S back here? Like, does it exist? And you have to do so. I will just say the statement, but then I can tell the others how we get to this conclusion. Basically, if you take omega bar, right, which is the product of these guys, you order the eigenvalues in descending order, you look at the first marginal. If that majorizes rho S, then there does exist such a V. Okay, so but this will be an extremely non-local guy. And so maybe that could be related to what you were saying. And so the way you get to this statement is basically because you want to work just on omega naught, then you are free to kind of choose a V which acts as a direct sum of these. And yeah, if you consider the Qtrit case, so it's like you take the total Hilbert space and you chuck it, so you cut it up into bits like this, where each JK is spanned by, so I'm giving the Qtrit example, right? Like I, then you do I plus J mod 3, because that's the dimension. And of the Qtrit, I plus K mod 3. Okay, so this type of basis choice, so here you had like a 27-dimensional object. Here you have 9 3-dimensional objects. Now the nice thing is that this, it has 2 nice properties. Each Vij cannot create correlations which are going to show up in the margin, right? The margin is always going to be diagonal. Secondly, when I sum over JK, I will automatically get the first margin, right? So that's nice. And basically the way then you proceed is you realize that by using this decomposition, and the state omega bar is also diagonal, right? So you want to do some V omega bar V dagger. And now we're saying we can write this down as some VJK omega bar JK V dagger JK. And these guys, if you look at them, really they induce some like some unistochastic matrix. Okay. On this guy, so I'm just kind of like grabbing these unitary contributions and like bringing the eigenvalues of the unitary together. You get this VJK squared here. And because this is a diagonal, then basically this unistochastic matrix is just acting on the diagonal. So effectively, if we call this like MJK, which is a unistochastic matrix, then all I have is a bunch of unistochastic matrices acting on some vector associated to here. So if we had this 27-dimensional vector, which we chopped up into 9 groups of 3, you would have like one group of 3, let's call it P vec jk, right? And then you can say, let me check the situation where all 9 unistochastic matrices are the same one. Just I'll check it out, you know? So let them be the same. Then you will have like mjk, or you will have m, which acts on the sum of these guys. And I told you that because of the choice of this basis, the sum over these populations is now the margin, the first margin of which I care about, right? So it will be m, kind of, let's call it 0, right? The vector of populations of the first margin. And when you have this situation, you have a unistochastic matrix multiplied by some vector, you have this Schurhorn theorem, which tells you that I can reach any Q here such that P majorizes Q. And that's basically the logic of how we get to this statement in this direction. Or what did we choose? No. So a V exists. No, indeed, in this direction. So we prove this direction. I will not prove the other one. It's actually easier, but for time constraints, I don't want to do it also. What's good to mention at this stage? How many people care about resource theory in this room, aside from Ben? Okay, no, you guys know. Then I will not bore you guys with resource theory. Maybe, yeah, I can maybe just talk very briefly about this work extraction protocol that I really glossed over. So, what do we want to consider? Maybe I'll wrap up here. So there is the system, it's in this box, I don't know what it is. Sorry, I am an agent, and I want to do some unitary to this guy to extract as much work as possible from S. But I don't know what it is. So what some people have shown, is you could do like a hard random unitary here. It doesn't do so bad, but it doesn't do great either. So this is a paper by, I think, I want to say 23, Safranek and Binder, about random work extraction protocol. So that's one thing the agent could do. But now we're saying if the agent has access to some like a probe system and also their memory, and they do our protocol a bunch of times, and they obtain the symmetrized state omega bar, then basically they have omega bar in their memory, right? They actually have m copies of omega bar. And they can use omega bar to say, what's the best possible, unitary to extract work from omega bar, right? So you obtain this knowledge, omega bar of the system. You've not perturbed the system yet, because it's a conditional unitary to extract the knowledge. And now you say, okay, so I think it's omega bar. It might be a bit different. I'm going to use U star to extract work from there. And it turns out that this is like basically optimal. So I mean, for this example, so imagine I give you in here 2 thermal states, let's say tau beta hot, tensor tau beta cold. So there's a temperature gradient across these guys. And I want to see the ergotropy of these, right? Like how much work can I extract from them? And now the difference between beta H and beta C, I'm going to call delta beta. And basically, if we had like, and let's do it like, so it's like 1. And if you have a single estimate, so the true value kind of does like this, where right here's like the maximum work you can extract. If I had one estimate only, then you basically get something like this. And if you had a symmetrized state, then what you get is something that very closely follows this. So symmetrization can give you access to a unitary that extracts work very well without having perturbed the system. So I'll just summarize and we can discuss if there are any questions. So we kind of went from this coarse-grained estimation picture to a unitary model. We did this because we want to keep track of the resources we're using to learn the state of the system, resources in terms of dimension of the probe, in terms of how many copies of the probe that we need to correlate with the state of the system. One resource we did not consider is the thermality of the probe. If the probe were at a high temperature, then the probe would be biased basically by the population of the probe, and what you learn will be impacted by that. That's a problem that was studied in this paper, but is not something we've done. Ideally, someone would put these two works together. And what's something we still want to do here? So here, of course, we've been able to learn the population on a single basis. For thermal states, that's enough. But what if now we have a coherent state, right? Like an X state, an X and Z, or whatever, pick your favorite state. Do you just do this protocol like, I don't know, something like L times, where L is the number of mutually unbiased bases you're interested in? Is there a smarter way to do it? Can we use like coherent interactions and information extraction to do better? These are all questions that I do not know the answer to. And they are questions I would like to investigate, because I think it's really good to build a like thermodynamic understanding of tomography. Sure, we have these like optimal tomography protocols with these like very big POVMs and so on, but what would it actually take for an agent to physically do them? I think this is one way to try to get at that. Thank you for listening. I'm sorry I got a bit confused at points. I hope it wasn't too bad. Okay, thank you.
Right, so here's we have time for question.
Yes, it's not a bit of a follow-up question, but anyway, I got confused. Do you assume always that the memory starts in like non-zero state?
So far, yes.
Because it seems to be that I think what I was trying to get lost in, there still seems like there's a constraint of how many non-zero eigenvalues you can have in the memory at the end. Because, and I think it's actually k squared rather than because each, after step one, your memory is in the pure state and your probe is in like some k-dimensional state.
This guy.
K.
Yes.
Then when you trace, whatever unitary you do, you've got to preserve, the total. I mean, whatever unitary you do, those k different eigenstates can only go into k different things.
So
each one, when you trace it, you k different.
I'm trying to follow.
So I feel like you're going to get rank k squared.
So I'm just trying to follow what you're saying.
Okay. After the step in memory and your probe,
So
there are a mixture of k different states.
So you have, let's say, this is the state of the probe after information extraction with these like p bar 0, p bar 1, blah blah, up to p bar k, which are k partial sums of d populations.
Yeah.
Now we are interested in the tensor product of sigma and 0, 0, d.
So this whole thing is a mixture of k.
Yeah, this is rank k, and this is rank 1.
Right? The whole thing is rank k. Now, obviously, when you do any unitary, it stays rank k globally.
Yes.
But now, you're right, you can get entangled with this.
Yeah.
Each pure state out of this rank k can give you at most k. When you trace over the system.
Yes.
Sorry, the probe. When you trace over the probe, it will only give you k rank k things on the probe.
Yes, but I mean, basically, if you had like, if you have P0, right? P0 is a sum of T things, or T0 things. So I don't know, it's like P0 plus P1 up to PT. And now, why, like, so I know that the sum of Ti from to K minus 1 is equal to D. So why, so I know that in here, maybe here, which is like a D by D matrix, I can split this into blocks of, this is a T0 by T0 block, this is a T1 by T1 block, this is a whatever, Tk minus 1 by Tk minus 1 block. I can exactly do this. There's like dots there, right? So if first I start out with P bar 0 here, and I know that P, like, so I have P bar 0, why can't I then like basically create a maximinimic state in this subspace with P bar 0? I'm just spreading that eigenvalue out uniformly across the subspace.
I mean, I guess you're requiring you to do constraints.
Yes, yes, but I don't know, you can.
I'm looking at this.
Okay.
I think there's a rank argument that means you can then get rank case there.
Okay, okay. I mean, I look forward. And I hope.
Could arbitrate the rank increasing operation.
Only volume dimension of anything by a factor, because each one.
But at least the example I gave you with the qubit and the qubit, also that one you disagreed with.
But then now we want to think. Yeah, but that was satisfying case left is less than. So it's fine. K was 2D with 3, so.
Oh, so there are situations.
Sufficiently large D.
Okay, so there are situations where it won't work.
Well, I don't wish you could get around it by having some mixing in the memory to start with, or having non-diagonal states. I mean, I'm assuming everything. You seem to want everything to be diagonal at the end.
Yes.
I think in that case, I might be wrong again, but I think.
I'm really curious. So yeah, let's discuss it.
Is all of these different T vectors of equal value? If I want to do like a single shot case and try to reconstruct my state as well as possible, there's an optimal T to do this?
So I did not mention this in the talk, but before this talk, I was going through an example I had for this like D and the qubit, where I had these two guys, like where these have these combinatorial factors here, and these are here. But they're both like, you have one T, so both have qubit probes, okay? The T vector here is 1D minus 1, the T vector here is D over 2, D over 2. And when I was checking this, I realized that these are actually equivalent states. So like so this is something I don't know. Like in the qubit case, it seems like whatever coupling you do gives you the same information. But here in the D over 2, D over 2 case, you need more estimates to get the same amount of information, because basically like D multi-choose this is larger than D multi-choose this. So it seems like if you have all the couplings, at least in the qubit case, if I give you all the couplings, you will get the same amount of information out. It might be that you need very many more couplings to do that. But yeah, this is something which I realized today, embarrassingly, and is a kind of a big deal, because it would mean basically, as long as I give you all the couplings for a given dimension, you will always get the same information out if I give you all the couplings. Of course, there could be many more states required, but I thought, as kind of maybe you were suggesting, that different T vectors of the same dimension will give you different fidelities.
Yeah.
In this case, it does not. It's weird.
So if there's no further questions, do you have a question? No. All right. And let's thank the speaker again.